Hey all, this has to be the very first video that I'll be uploading on my respective YouTube channel. And most of the videos that I'll be dropping here in the time strands, you would largely revolve around tech and the programming concepts. And to begin with, and just to begin with, because in the times to come, we'll be doing some other different things as well. Today we would be solving a TSC problem, a problem which is hosted on LeetCode platform. And the programming languages that we would pick to solve this problem is something which is in sync with what most of the people or most of the smart people around the world prefer, which is Java and C++. And the choice between these two is something very subjective, and it largely depends upon the need of the developer as of what he actually wants to do. If speed is something which is more important for the programmer, then perhaps he should go along with C++ because of its low level nature and its ability to directly communicate with the hardware. This is something which allows to be able to build more efficient algorithm in terms of time. So that is something. If speed is something which is important for the programmer, so he must go along with C++. While even if he choose Java, it doesn't make a lot of difference because still, even if you think in terms of time complexity, even in that case, there is no substantial difference between these two. So feel free to choose any one of them and start. That is more important, that we should be able to start as early as we want to. So now let us move to the problem that we have thought of solving today. Okay, so the question that we have is 204th question of LeetCode and is titled as count prime. So basically this program is asked us to develop a program that will receive an integer as a parameter and should be able to return the number of prime numbers which falls below that number. For example, if you have a number 10, if the program receives a number 10, then you should be able to repeat or return the number of prime numbers that falls below that number. For example, if you have a number 10, then you should be able to generate 4 because it has 4 prime numbers which are less than 10, which is 3, 2, 4, 5, and 7. So these are the 4 numbers. That's why the output should be 4. Similarly, if we have an input of say 20, then you should be able to generate all the prime numbers which falls below 20. So that's essentially the basic functionality that our program has to offer. Now, if you look at the constraint, because it might appear like a very straightforward problem, a very pushy problem as such, which probably would be having a very simple solution. But if you just look at the constraint, actually, before looking at the constraint, let's just think of the kind of approach that we would be having. We would be having the first basic or the most rudimentary at the brute force approach that we could think of to solve this problem. Whenever we start programming, one thing which we definitely learn is that how to figure out if the number passed into our program is a prime number. Each one of us probably would have learned that. For example, if number 5. So most of us would have learned a program wherein the program checks if the number that is received is a prime number or not. So probably would have learned that we will initiate a loop or loop or while loop. We'll run it from 2 to say n-1. Why so? Because for a number to qualify as a prime number, first thing is that it has to be a positive number. Second thing, it should have no other factors other than one and the number itself. If it has any other factors, that is, if there is another number which divides the number and leaves no remainder, then that number is not a prime number. And we'll initiate it from 2 to n-1, and we'll check that if n is when n is divided with any other with I is what is the correct value in this loop, generates 0 or 1. If it does, which means that there are other factors or there are other numbers which produces no remainder when they are divided with the respective number, which means that is not a prime number. So I think this is something which most of us would have learned. This is probably the most basic program that we build once we start or once we take our first step into the realm of program. So most of us do know this, and when we think of our problem in this very context, then the one or probably the basic or the most rudimentary approach or the most rudimentary thought that comes to mind is that let's say that we'll build a main method, we'll build a supported method, say is prime, and in this method we'll have the implementation wherein actually it will receive an integer. It will receive an integer, and then in the block of this problem we'll be having it will be having a sort of implementation. This implementation would be able to figure out if the past input in this program is a prime number or not. Then we will have a main function or a supporting function that would say now this function has to have some parameters as well. Okay, it will then we will initiate a loop inside that. Let's say for loop from 2 to the number itself, which is n minus 1 in this case, because we want to produce all the numbers which are strict. We want to produce all the prime numbers which are strictly, or basically we want to count all the prime numbers which are strictly less than n, so n minus 1. Or actually, yeah, it has to be n minus 1. And what we could do is that we will call our supporting method that we have done, that we have created below, and we will pass the correct value. And it should be able to give us, if we should be able to let us know, or would provide the information that if that particular number in the iteration is a prime number. So this is the most basic approach, and this should be able to work. This should work. This is logically correct, and so this probably would be accepted by the program. It is accepted as well. So this should be able to deal away with that problem. But the problem with this approach in the context is hidden in the context, is hidden in the constraints that have been provided. If we see, then it has been mentioned that n can be as big as 5 into 10 raised to the power of 10 raised to the power of 6, which is, it could be like it could be 10. It has been mentioned 5 into 10 raised to the power of 10 raised to the power of 6. It can be as big as this. Now, if you think of this, problem, then the time complexity that this problem would be, this solution would be is a big O of n square, which is that for each input that you will receive, it has to do n raised to the power of 2 operations. Which is that if the input is as big as this, then the number of operation that will have to make on it is something like this, which will result in around 2.5 into 10 raised to the power of I guess it should be 10. It should be 10 to the power of, I guess, 11. Could be wrong, but I suppose it has to be like this. So it would have to carry out these many operations. Now, even if we consider that one operation takes 1 nanosecond, then upon having going through all sort of say calculation, we'll be having around, we will end up having, I guess, 250 seconds. 250 seconds, which is above 4 minutes. So it would take 4 minutes for our algorithm to run and be able to generate the output. And most of the coding platforms, be it CodeChef, CodeForces, or LeetCode, does not actually provide you that bandwidth, wherein, or absolutely, it has to finish within a couple of seconds. If it does not, so then you will get a time exceeder, or it's a highly inefficient program to do away with this problem. So this is the problem with the rudimentary or the most brute force sort of approaches that we think of. They're not efficient programs. They cannot handle the large input, or the very large input. When they receive large input, they take a lot of time. So if you have a platform which is powerful enough, then even the brute force approaches should be able to do away with that problem. But generally, we don't prefer them, and we shouldn't actually, because if we can have better alternatives, then we should stick to them. Great. Now let us think, or let's try to build a more efficient solution of this. Now there are multiple algorithms that you could think of. One which is very popular is something called sieve of Eratosthenes. Yes, this is how it's pronounced as well. Sieve of Eratosthenes. Now let's. What actually it does is that it will iterate from. It will do the same thing. It will iterate from 2 till n minus 1 in our case. But the thing it will do differently is that once it has found that if a number is prime, for example, we know that 2 is a prime, then what it will do is that it will set all the numbers which are multiple of prime numbers as non-primes, which is obvious. Let's say we have a number 3. What are its multiples? We get 6, we get 9, we get 12, we get 15, we get 18. So we can see that all these numbers are not prime numbers. They won't be as well, because if 3 is because if you think of 3 is 6, then there may not be even 2 is there, which is a factor of 6. But even if you suppose that there are no other factors except 1 and 6, but since 6 is a multiple of 3, which means that this number won't be a prime number. So a multiple of any number won't be a prime number. This is something very sure unless that number is 1. So the multiple of any number will be a prime number. This is the thesis, or this is the premise on which we'll be building our program. We'll be taking the prime numbers and we'll be setting all the numbers which are multiple of that number as non-primes, and eventually we'll calculate which all numbers are left which are primes. So this should be deal away. This should be able to solve our problem with a very less time complexity. Probably it would have a time complexity of I guess it will have a big O of n log n, and this would be much more or substantially less than the amount of time it was taking, or our brute force approach was taking. Okay, so now let us build an actual working solution for the respective problem. Now we had built the basics as of how our program would have an approach and have thought of the premise on which we'll actually be solving the problem. So now let us start building a working solution for this. Before that, let us handle the edge cases. So what are edge cases? We know that edge cases are those cases which are those extreme values that require some specific care, because our algorithm most of the time is unable to address those as well. So in this case, we know that if the number is, or if the input that we receive is less than 2, then we know that if the number that we receive is less than or equal to 2, then we know that there are no prime numbers which are less than 2, and any other input which is below than that. So we can directly return 0 by default. We need not to think of that. Now we'll be creating a vector. And when we are creating a vector in C++, we use standard namespaces along with that scope resolution operators, and then we'll give a name to it. And now we'll call on the constructor of the vector. Now the constructor of the vector consists of two parameters. One is the size. Now the size will set it to n because they want to include 0 as well. And the second input will be the initial value that we want to set for all the elements or all the indexes in the prime vector that we have created. Now we'll create a counter which will keep the count of the prime numbers. Now at most we can have n number of primes, less -2, n -2, because 1 and 2, or because 0 and 1, we know that for sure these two numbers are not prime numbers, so we can have this. Now we initiate a loop. We'll declare the current element I, and we'll initialize the value 0 to it. We'll set the condition as I till I is less than the square root of s, till square root of what, n, and upon each iteration we'll keep on incrementing the value of I by 0, by 1 actually. Now why have we set this condition is something we may think of, or you may wonder that why we continue the loop only till I is less than the square root of n and not n. It has a very simple actually underlying concept, because whenever we are factorizing a number, let's say that if you have 16, then the two factors that you will have is 4 into 4, or it could have 1 into 16, or you would have 2 into 8. So if we get the square root of 16, which is 4, and we know that if we get the square root in the square root, we'll get the number. So 4 into 4 is 16. Any other factorization, which could be 1 into 16 or 2 into 16, one thing we can observe that one factor is less than the square root and one factor is greater than the square root, which means that if a number has to be, or if the number is not a prime number, then there will be a factor which either would be equal to the square root of that number or would be less than that. So this is the common observation we are able to conclude, and we are just applying that we will run our loop till the square root of the n, and if n is not a prime number, in that case we would be able to find a number within this range that is able to divide the number and still be able to leave no remainder, or be able to generate a remainder 0. So that's the underlying concept on which we have applied this. Now we will initiate our loop and we will check that if the current element, which is I, is true. If it is true, then we'll create another loop inside the if block, and inside that if block we will have another variable, say integers I. We will declare current element j and we will initialize the value I into it, and we will run this loop till n, and we will increment the value of j by I, because we want to find out the multiples of I. So what actually this loop will try to do is that it will get the multiples of it will first the outer loop will figure out if the number is prime number or not. If it is, then our inner loop will find the multiples of it, and we will set those certain indices as false, and eventually we'll be able to calculate the number of prime numbers that are within that range, and we'll return that. So this is something which we'll do. Now, why are we doing is this? Why are we having this G is equal to I into I and not I? Is again we can look, for example, let's say we have a number 4, then square of it would be, if we have a number 4, then square of it would be what? Would be 16. Now, what are the other multiples of 4? The other multiples are 8, 12. Are they not already being taken care by 2? Obviously, 2 4s is 8 and 2 6 is 12. So when we will be finding out the multiples of 2, it would be able to set the element which is 8 to non-prime and the element which is 12 to non-prime. So it should be able to deal away with that. So we can directly start from the square of that number, because all the numbers which are less than the square of that number and are multiple of that number would already be taken care by the smaller numbers or the number below that. So that's the reason we have we had this expression, or we had initialized the value of j as I square. Also, in this way we can have this as well. I square I, just a basic math, right? Now we'll initiate, or we will build the, say the body of the loop, and in that we'll again check that if the current element is prime or not. Why? Is something you should actually question or should wonder that why. Because let's say, similar analogy, let's say 16, because we know that the square of 4 is 16, and we also know that 16 is a multiple of 2. So when we would be at 2, when the current element will be 2, and we will be setting all the multiples of 2 as non-primes, then we will set 16 as primes, as non-prime, and we'll be back to 4. Now 4, 2 will land on 16, and if the number is already non-prime, then if we again set or try to set it as non-prime or as false, then still would be able to do so. But if we are also decrementing or incrementing our counter along with that, then we will have a LHS reading. That's why we are avoiding. That's why we'll be checking. We'll again inside our inner loop, inside the inner loop as well, we'll be checking if the number is prime or not. If it is prime, then we will set it as non-prime, false, because we have set true initially. Here it should be j, false, and also will be decrementing our counter. So each time we have found the multiple of a prime number, which means that number is not a prime number, so we'll decrement our counter by 1. So this is the basic structure of a program, and eventually we should be able to return the counter, which actually would be holding the number of prime numbers that we'll be having strictly less than n. So this is something which you have to do. Now let us run our program. We are done with it. I think it should be able to solve our problem. Okay, we can see that there is some issue I can see, which is that I haven't set the data type that our vector will be having. That is, what sort of data the vector will be actually storing. It has to be a boolean, because we have already set the initial values of all the elements as true. So the data type it will be holding is a boolean. Make sure that in C++ we use bool as a data type, and when it comes to Java, we use bool, that is boolean. We write boolean like this in Java, but in C++ we write only bool. And one more thing which I'm able to see, or one bug which I'm able to find out in my problem or in the program that I've jotted, is I has to be initialized as 2, because we know for sure that 0 and 1 are not prime numbers, so it doesn't make the difference. Now let us submit our problem and see if it works as we want it or not. I think we should be able to deal away with our problem. We should be able to, yeah. So we can see that it's a quite efficient program as well. We have been able to beat the 70% of the folks herein, and so yeah, it's a quite efficient problem. It has solution. It has been accepted. We can run it as well, but we have already submitted it, which means that we have already tested it for more number of test cases than that of because here only 3. It would be checked. This algorithm specifically would only be tested for 3 test cases, wherein here it was tested for multiple test cases. So there was a test 5, which consisted of multitude of test cases, and this whole of our program went through multiple test cases. Okay, now we have solved it. We'll copy it. Now we will solving it in Java. Okay, one thing which we know, when we are trying to solve the problem in Java as well, the syntax is very same to that of C++. Only there will be minor differences. So let us do that. Now we have copied the same code. The differences are we don't use a semicolon after public, and there is a different methodology to declare array or a vector, because the difference is that vector is a dynamic array, which is that the size is not fixed. We can increase or shrink the size of the vector. Where in case of the Java, if you are using array, then that functionality is not available. We don't actually need it still. We'll have this edge case statement. We'll only remove this declaration part, and we'll declare it differently. Boolean, and this is the method. This is the way we declare an array. We'll name it prime. We're not changing the name of the array, because if we do so, then there'll be problem. We'll need to change this identifier throughout the program, which we don't want to do for now. And we'll have it as a new keyword we use whenever we are creating a new, or whenever we're creating an instance, or an object. Object is an instance of any of the class. So new, and we are now, we need to set the size of the array, which is n, we have discussed earlier as well. Now we need to fill, or we need to set all the elements of the respective array at initial value, which is this arrays dot fill, and we will set now this is the method which is used to give a initial value to all the elements, or to all the indices of the given array. It receives two parameters. First, the array is going to work on, which is the prime in our case, and the initial value we want to set to. So that's how it should work. Now let us see if it works as well or not. I think it should be able. It should do. This was the only minor difference that is usually found in Java with respect to that of C++. So we can see this solution has been accepted as well. So yeah, we have managed to solve our problem in both the languages, which is Java and C++ as well. There are minor differences between the syntax of both of them, but the working of the loop conditionals is very similar to that of the Java. Is actually identical to that of the Java. So feel free to choose any one of the language, and this is just the starting. We'll be solving more such problems in the days to come. And thank you so much.